Hello everyone, and thank you for being here. My name is Douglas Blumeyer, and I'm a Xenharmonic composer and theorist from San Francisco. I hope you'll forgive my choice to theme my talk around the 1999 sci-fi action film The Matrix. You'll understand why I made that choice soon enough. Without further ado, the topic of my talk today is Regular Temperament Theory, or RTT for short. RTT is a popular subtopic within the broader field of microtonal music theory, and today I plan to give you a crash course in it. Let's break down those three letters first. Starting from the back, theory. Yes, the ideas I'll be presenting today are still quite new. Their roots go back hundreds of years, but the modern paradigm of RTT dates from the end of the 20th century, around the peak of our civilization. Temperament. Temperaments exist in the wide space of possibility between just intonation, or JI, on one extreme, and equal divisions, or ETs, on the other. With JI, we refuse to compromise on the tuning of the prime harmonics. The building blocks of harmony must stay pure. This sounds wonderful, but it means we need as many different step sizes as we have primes. This can be challenging when it comes to choosing scales, composing music, building instruments, notating pitches, etc. Pretty much everything. With EDs, instead the thing we refuse to compromise on is having a single step size. Here, we take this one simple and convenient step size and do our best to approximate each prime using it, and it alone. So what temperaments do is find a middle path. There is a way to use fewer step sizes than with JI, without limiting ourselves to only a single step, as with an ED. And that's all it is, really. Doing it this way, we can end up with a best of both worlds situation. Recognizably close approximations of primes, but not too complex to use. If, that is, we learn how to use it. And that's why we're here today, for your training. This temperament space in the middle is fondly referred to by members of the RTT community as the middle path. It was given this name by Paul Ehrlich, a fellow presenter at the symposium, and one of the co-founders of our modern regular temperament paradigm. And so the final word of RTT to look at is regular. This word is important because it distinguishes this theory from other tempering strategies like well temperaments. We're only going to be talking about regular temperaments today, though, so from this point I'm just going to call them temperaments. I should at least give you an idea what regular means, though. Regular basically means that for each prime approximated by the system, there is exactly one interval in the temperament that approximates it, not many different intervals. That's for temperaments like well temperaments. And this brings us, at last, to the theme of this presentation. You know the question, same as I did. What is the matrix? In RTT, the matrix has you. The matrix is everywhere. It is all around us, even now in this very room. But I don't mean the fun post-apocalyptic kind run by killer robot overlords. No, I mean these horrifying types from math books, the boxes with a bunch of numbers arranged in them. Now, you've probably never seen a matrix on sheet music or in a digital audio workstation interface, and maybe not even in a music theory textbook, so you may then wonder, how could we use boxes of numbers to help us make interesting new music? Well, here's the answer. RTT uses matrices to show exactly how temperaments stretch and compress the prime harmonics in order to achieve new and unusual harmonic effects. Would you like to know what those are? Unfortunately, no one can be told what the matrix is. You have to see it for yourself. So let's dive right in. Today we're going to be looking at a total of 4 different types of RTT matrices. Specifically, we're going to look at intervals, mappings, generators, and the primes tuning map. Putting these together as an acronym, we could call it PGMI for short. Believe it or not, when you put these 4 matrices together, even though this looks like a ton of complexity, all of this PGMI stuff resolves down to just a single number. And what is that number, you ask? In this case, it's about 193 cents. This is the answer to the question, what is the size, in quarter comma, mean tone, of a small whole tone? By the end of this presentation, we'll take you all the way through the PGMI system. So at this point, you might be thinking, whoa. Or you might be thinking, this feels a little weird. Well, the type of math involved in these matrix calculations is called linear algebra. So please try to relax. We are going to learn a little math. I promise, though, once you get used to matrices, you'll find that they are powerful and efficient tools for understanding some wonderful music. So just free your mind. And let's start at the beginning. First, we'll look at intervals. I do mean interval in the everyday musical sense of a distance in pitch, from one pitch to another pitch. These 3 numbers are a special way to represent a JI interval. In this case, that JI interval's ratio is 10 over 9. This is that same small whole tone interval we looked at in the big example a moment ago. If you're not very familiar with JI, all this means is that it's the interval between two pitches, where the higher pitch's frequency is 10/9 the frequency of the lower pitches. When we choose a base frequency, such as in this case with 110 hertz, we could say our root pitch was 9 times this, and the higher pitch was 10 times this. And so the interval is just the distance between them. Like the famous digital rain effect for displaying the code of the matrix, the numbers of an interval are arranged as a column, up and down, not side to side. We read them from top to bottom, so this interval is read 1, -2, 1. This matrix has got 3 rows and 1 column. When we've got a matrix with just 1 column like this, we use a special name for it, a vector. And these 3 numbers on the inside, we call those entries. You could say that they have entered the matrix. But what do these entries mean then, individually? How could it be that 1, -2, and 1 expresses 10/9? There must be some important information missing or assumed here. And indeed there is. But what we're missing are the units of this vector. So what are the units? Well, if the binary numbers 0 and 1 are like the units, or maybe we could better call them the building blocks of computer code, then think of the prime numbers as the building blocks of harmonic code. Any interval can be described as a product of these primes, and it's a well-known fact that the prime composition of intervals is a major part of how they sound. So the entries of these interval vectors are telling us the counts of primes. So when you see a prime count vector like this, shown without any unit labels, you can assume what they are. The primes, in order, not skipping any, and from the beginning. So let's try labeling this one. Just start with the lowest prime, 2, and then work your way up, prime by prime. Next one is 3, and then we have 5. In this case, we have only 3 entries in our vector, so we only make it up through the first 3 primes, 2, 3, and 5. And so this vector answers the questions. How many 2's are there? 1. How many 3's are there? -2. How many 5's are there? Again, 1. You may wonder what could it mean to have -2 3's? Well, it does not mean to subtract 3's. These primes are all going to be multiplied together. So in mathematical terms, the entries of this vector, the counts, are really exponents. All right, so they're multiplied together. 2 to the first power and 5 to the first power. Those ones are easy. Anything to the first power is just itself. So we can just get rid of those exponents. But 3 to the -2 power is trickier. The negative part means to put the result in the denominator. That is, we now need to start thinking of our number no longer as an integer, but as a fraction, or a rational number. For now, it's all over 1. That is, there's nothing of any value in the denominator yet, but we can get rid of the negative sign in the exponent by putting 3 on the other side of the dividing line. And we'll just squish that top together a bit then. All right. So now the remaining 2 part of the exponent just means that the 3 is squared. That's 2 3's multiplied together, 3 times 3, which is 9, and 2 times 5 in the numerator is just 10. And so that's how we end up with 10/9. It might seem like a lot of work the first several times you work through a prime factorization like this, but if you use it enough, it'll eventually become second nature. But who cares? Why not just use 10/9? Or why not use a decimal like 1.111 repeating? All 3 of these numbers represent the same exact amount. There are pros and cons, though, to each way of writing it. The decimal style is good for getting a quick sense of where this amount is along the number line, between 1 and 2, but clearly much closer to 1. But this way of writing the number shows us nothing about how it's the ratio between the numbers 10 and 9, which sometimes we might care more about. And the fractional style is good for that. There are certainly good reasons why we go to all this trouble to view numbers as their prime factorizations in RTT. But to see how, though, we're going to need to set them aside for a minute and learn a bit more about our next type of matrix. And that's the mapping. Here's an example mapping. Our previous matrix had only 1 column and 3 rows. This matrix, you'll notice, has 3 columns and 1 row. When a matrix has only a single row, we can use a special name for it, a map. It's easy to remember because it's like the word mapping, and this is still a mapping, but with only a single row, it's the smallest possible type of mapping, so we use a smaller word. Just like it was for an interval vector, the individual numbers on the inside of a map are called entries. Okay, but what is a map? What is it for? Perhaps the best way to answer that question is with another more direct question. What are its units? Well, perhaps unsurprisingly at this point, they are related to the prime numbers. And unless specified otherwise, we're safe to assume these entries are labeled with the prime numbers starting from the beginning in order, skipping none. But the units aren't exactly the primes here. They're steps per prime. So each entry lets us convert a different prime into a step count. Specifically, it tells us there are 12 steps to reach prime 2, 19 steps to reach prime 3, and 28 steps to reach prime 5. You may have realized by now that this is actually the map for 12-tone equal temperament, or 12ET for short. The standard temperament that almost every guitar, piano, and computer synth in the world is tuned to. 12ET is an equal division, as you may also know. In other words, it has only one step size. This corresponds with the fact that its mapping matrix is just a map, that is, has only a single row. And you may now be wondering, but wait, I thought this talk wasn't about EDs, I thought this talk was about RTT, the middle path. Well, an interesting thing is RTT tools don't break down at the edges. RTT works for EDs and it works for JI. In fact, the only difference is the number of mapping rows. With one row, it's an ED. With more than one row, you're looking at RTT, at least until the point that you have as many rows as you have columns when your mapping goes square. Then you're using JI again. For now, we're going to continue looking at an ED map because we've got to cover some basics, and EDs are simpler to teach those on. But we'll work our way back up to RTT as soon as we can. For now, the important thing is, now we can answer the question, what is this map for? Its purpose is to tell us for a given interval how many steps it is in this temperament. Let's try it out on an example. How about a perfect fifth, 3/2? Well, it's got a 3, so that's 19 steps up, and it's got a 2, but it's in the denominator, so that's 12 steps down. So 19 minus 12 is 7. 7 steps. That checks out, right? 7 keys on a piano or frets on a guitar to a perfect fifth? Right. And now how about a major third, 5/4? Well, it's got a 5, so that's 28 steps up, and it's got a 4. Well, 4 is not a prime number, but it's equal to 2 squared, so that's 2 2's, and they're in the denominator. So that's 12 steps down, twice. So that's 28 minus 24 equals 4 steps. That checks out too. But are you starting to see what's going on? Wouldn't it be more helpful if we just had these intervals in their prime factored form already, as prime count vectors? Yeah, that would be nice. For starters, here's 2/1, but as a prime count vector. So all we're really doing is matching up numbers in the two matrices. So this answer is 12. And here's 3/2 again, but as a prime count vector this time. And so the answer is 7. And here's 5/4. Again, the answer is 4. With these simple examples, we can practically eyeball the answers, but we can also see that it's quickly getting trickier, and it would get out of hand pretty soon if we went much more complex. Fortunately, there's a generalizable method for doing these sorts of calculations in a streamlined way. They come up so often in so many practical situations, not only in RTT, but in all sorts of sciences and engineering disciplines, that math has defined a handy operation for them. And it has a name. That name is the dot product. And as you might expect, you can represent it with a dot between the two matrices. Though if you just smush the two matrices close enough together, it tends to imply that you should dot this. To demonstrate how the dot product works, let's compare it with how Neo defeats Agent Smith at the end of the matrix. Oh, spoiler alert! Sorry. Alright, so we've got this horizontal thing, the map, which is like Neo, and it matches up with a vertical thing, the vector, which is like Agent Smith. In this case, Smith is the vector we looked at earlier, the one for 10/9. So the map flies into the vector and merges with it. It's a bit crowded and uncomfortable in there at first, with both of them occupying the same space, so we multiply together each pair of matching entries. This way each pair gets reduced to a single number. We're getting there. Now we just need to add together all of those results, and blam! We're left with the 1. Well, in this case the actual answer is 2, but the point is it's just one number. And so 12ET's approximation of 10/9 is 2 steps. Congratulations! You're already doing linear algebra. Alright, so what I'd like to do next is replay that dot product computation we just did, but this time around, instead of comparing the numbers with images of people blowing up, let's compare them with what happens with their units. But we're going to look at the units a little differently now. Labeling the prime units with numerals 2, 3, and 5 was an okay way to ease you into this, but it's going to get confusing pretty soon with all the other numbers on the screen. So better to start using a more reasonable unit symbol. Let's use P for prime. So prime 2 is actually prime subscript 1, or P sub 1, and prime 3 is P sub 2, and prime 5 is P sub 3. Alright, so we start out with primes in the vector, and steps per prime in the map. So you could imagine if we have information that's in terms of these prime units, when combined with steps per prime units, then when you multiply them, the primes cancel, since for each pair one is in the numerator and the other is in the denominator. And so we end up with just a bunch of values in terms of steps. This is powerful because we went from having information with 3 different units, 3 different types of primes, to having information that's all in terms of a single unit, steps. Once all the information is in steps, then we can lump it all together into a single value using addition. And so finally, our answer is 2, but it's specifically 2 steps, steps of 12 ET in this case. So what am I saying? That you can do the dot product that you can do the dot product now? Well, really what I'm saying is, when the time comes, you won't have to. That's what computers are for. As I said before, the dot product is a very common operation, so it's available in math tools. Personally, I use a free online math tool called Wolfram Cloud for computing dot products. Suppose I needed to do this dot product. Now, I know I could do it, but I don't really want to do all that busy work. All I need to do is type this into Wolfram Cloud, push enter, and voila, I get my answer, 1. Now, something in particular I want you to notice here is that the dot product only works when the map and the vector have the same entry count. What if our vector had 4 entries? Then the last entry has units of p sub 4, or in other words, the count of prime 7s. But our map doesn't tell us how to convert from prime 7s to steps. We just don't know. Or if our map had 4 entries, but our vector only had 3, then, well, I guess we could assume the extra entries would all be zeros, but technically we don't know what those are either. So it's simplest for now to just say when we do the dot product, the entry counts should match. Another way to say this is the row count of our vector on the right must match the column count of our map on the left. The convention when writing out the dimensions of matrices is to write the row count first and then the column count. So we can say that our map is a 1 by 3 matrix, and the vector is a 3 by 1 matrix. This row column convention for writing matrix dimensions has a convenient effect whenever we're thinking about doing dot products. We know the columns on the left have to match the rows on the right, so the dimensions that must match are the ones that are in the middle, right next to each other. Nice. It may also be helpful to view these matrices as abstract boxes, so I'll put those up here too. In this case, the outer dimensions also happen to match, but they don't need to in general. For example, it's perfectly fine to do dot products between a 1 by 3 matrix and a 3 by 2 matrix. All this really is mapping 2 intervals in one go, knocking out 2 at once. You could break down the operation like this. We just do the dot product with the first column vector as we would normally, and then do the dot product with the second column vector as we would normally. So we do the dot product twice, therefore we get 2 answers. So here our result is not a single number, it's actually another matrix. Just a really small one with only 2 entries, 1 entry for each dot product that we just did. I've skipped over actually computing the dot products here because we've already done both of these examples today and I remembered the answers. So at this point what we're doing is called matrix multiplication. 2 matrices go in, 1 matrix comes out. So matrix multiplication is a slightly more complicated operation than the dot product. Matrix multiplication uses the dot product. Each time you do matrix multiplication, you will do the dot product potentially many times. In fact, you could think of matrix multiplication like doing every possible dot product between the 2 matrices and then arranging the results in an organized way. And regarding that organization of the results, here's a cool effect. The outer dimensions tell us what the dimensions of the output matrix are. So you can imagine the matching inner dimensions cancel out, and then the outer dimensions squeeze in closer together, and there you go. So in this case, multiplying a 1 by 3 matrix and a 3 by 2 matrix, the outer dimensions are 1 by 2, and so those are the dimensions of our result. We can even see how back when we did the original 1 by 3 times a 3 by 1 matrix, why we got a single number as our output, because another way to think of that result would be as a 1 by 1 matrix. Well, so now, what about if we multiplied a 2 by 3 matrix and a 3 by 1 matrix? In this case, we still do a total of 2 dot products, so our output matrix still consists of just 2 results, but this time they're arranged as a stubby little column rather than as a stubby little row. Previously we dotted 2 different vectors with the same map. Now we're dotting the same vector, but with 2 different maps. And so here at last, we're finally ready to make the transition from mere EDs to RTT. In other words, let's look at a mapping with more than one row. This is the same mapping we looked at toward the beginning of the presentation, the one for mean tone temperament. This mapping has 2 rows, which means it has 2 different step sizes. And as soon as a temperament has more than one step size, we usually stop calling it just a step. We use a fancier word now, and that word is generator. So This temperament has two generators, again, one for each row. And just as with the one-row mapping, the columns correspond to the primes. So remember in RTT, the middle path, the goal is to use something more than just one step size, but something less than a different step size for each prime. In this case, you can see that we've gone from having 3 primes to having only 2 generators. You'll recall that the units of the entries of an ED map weren't simply primes, but rather steps per prime. Similarly, the units of an RTT mapping are generators per prime, so each entry relates a different combination of prime and generator. In other words, we know for each prime how many of each generator approximates it. And so these entries tell us that prime 2 is approximated by one of the first generator, prime 3 is approximated by one of each of the generators, and prime 5 is approximated by 4 of the second generator. So let's think about this for a moment. Can we figure out, just from the setup, about what the sizes of these two generators are? With an ED, that would be easy. The first number says 12, so we know it's about a 12th of an octave. We're dividing this pitch by 12 in logarithmic space, which is why I've written it as a 12th root. If that doesn't quite make sense to you, don't worry about it too much. It's not important right now. The point is, as soon as you have more than one generator, their sizes are no longer obvious from an absolute perspective. That's because their sizes are now partially in terms of each other. They influence each other. So it becomes sort of a puzzle to figure them out. It's trickier, but we can still do it. Start with prime 2. So if the approximation of prime 2 is accomplished using only one of the first generator and nothing else, that means that no matter whatever else is going on here, the first generator must be approximately prime 2. So that part is simple enough, but now we have to build on it. So now if prime 3 is approximated by each of those generators, that's a 2, plus one of the second generator, then we basically have an algebra problem to solve here. 2 times x is 3. Solve for x. So that means the second generator approximates 3 over 2. So the second generator is a perfect fifth. Applying this new understanding to the last column, we can see that what this matrix says is that this is the temperament where prime 5 is approximated by 4 perfect fifths. And that's one way to define mean tone temperament. So what we have in these 6 numbers is a compact and objective way to encapsulate the concept of mean tone temperament. Mean tone is an important temperament. It's rather simple, but it does a great job with 5-limit harmony. That is, harmony using only prime harmonics up to prime 5. And for this reason, it has enjoyed some historical use. The historical users of this temperament understood how mean tone modified the relationships between the primes in this way, but the formalization of it in this matrix form didn't really start happening until the 90s. That's the defining moment of the modern RTT paradigm. As soon as you start codifying these things as matrices, it's relatively easy to conduct automated searches for other temperaments of interest. Other matrices people might have overlooked historically, but given the numbers, are in the same ballpark of sounding interesting without being too complex. This temperament, for an example of that, is called porcupine. Giving it a similar analysis, we can see that its first generator is clearly an approximate prime 2, just like mean tone. But its second generator is totally different. This is telling us that in order to approximate prime 3, we actually go up 2 of the first generator, overshooting 3, because 2 times approximately 2 should get us to approximately 4. And then we go back down by 3 of the second generator to get to the approximation of 3. So again, we can solve for the other generator. 4 divided by x equals 3, so x is 4 over 3, a perfect fourth. Except it's not quite that simple, because we need to split that 4 over 3 perfect fourth into 3 equal logarithmic parts. So each of those comes out to about 160 to 165 cents. And then we have a similar thing going on with prime 5, where we overshoot it, going all the way to 8 over 1 in this case, because 2 to the third power is 8. And then if we step back by 5 of that same 160-something set step, then that gets us close to 5 over 1. And that's porcupine. So porcupine is cool because it still does a good job of approximating familiar 5-limit harmonic relationships with this setup. But melodically, with those 160-cent steps, it behaves in a way you might be totally unfamiliar with. And mean tone and porcupine are just 2 ways we could do this. I could go on, even only about temperaments that are just like these 2. 5-limit with 2 generators, where the first generator is an octave. Here's just 7 more such temperaments, but there's plenty more of interest for various reasons. And some of these don't even actually approximate the primes that closely. They do it just well enough so we can still recognize them, but then they twist them into bizarre and surprising relationships. Whatever the case may be, any regular temperament can be represented with a mapping matrix like this. Okay, I need to rewind a bit now, though, because remember when we did that matrix multiplication a bit earlier, and we saw that mean tone took our small whole tone, represented by the prime count vector 1, -2, 1, and mapped it to a smaller vector with entries -1, 2. If not, that's okay. We were focusing on other things at the time, but I want to pin this thing down now. So remember again that this output is just the result of a series of dot products, the results of the two possible dot products between these two matrices. Those are -1 and 2. I'm not going to work through these dot products in detail like we did some other ones. Perhaps at a glance you could see how the first one works out and the second one. What I really want to touch upon here now is, though, what's up with that smaller vector? What would we call this thing? Okay, I'll tell you what. It's a generator count vector. If a JI interval is a prime count vector, and a temperament mapping is a generator count to prime count matrix, its units are generators per prime, then the result of multiplying them together should be a generator count vector. This tells us that in mean tone, a 10/9 is approximated by one approximation of your octave, but down, and then two approximations of your fifth back up. And here's how that would look in Wolfram language. You can see that the syntax got a little trickier from back when it was just a map and a vector, but it's no big deal. You get used to it quickly. Okay, now we're ready for our next matrix, the generators matrix. Here's an example generators matrix. What this matrix does is it tells us the tunings of our generators. You can think of a generators matrix as a list of interval vectors. Just like interval vectors, the rows correspond to the primes. Let's slice it up one column at a time then. Each column is a vector for a different generator. So this first one, 1, 0, 0, is just the interval 2/1. And the second one, -1, 1, 0, is the interval 3/2, an octave and a fifth. So these generators could work okay for mean tone temperament then. Okay, but how do we use these generator matrices? Perhaps, unsurprisingly, we can do some more matrix multiplication, but multiply this with what? Well, do any ideas occur to you upon noticing that these columns are associated with generator 1 and generator 2? How about one of those generator count vectors we just learned about? The one for 10/9, perhaps? Okay, so generator count vectors are always going to have one column, right? They're vectors, right? And they'll always have one row for each generator, aka one entry, one dot product per generator, which is perfect because the generators matrix is always going to have one interval column vector for each generator. So the inner dimensions will always match up and we can multiply them. But then what does the answer give us? A new vector. This is a PC vector again. So as for our units, we started in primes, we went to generators, and now we're back to primes? Don't worry, it's not deja vu. It's not a glitch in our matrix. It's not the same cat. That is to say, it's not the same vector. We're back to prime counts, yes, but the temperament has changed their quantities. -3 to 0. So that's 2 to the third power, which is 8 in the denominator, and 3 squared, which is 9 in the numerator. 9/8. So we've changed 10/9 into 9/8? Well, why would we do that? Well, let's rewind a bit. How did we get here? We got here by starting out with 10/9 as a PC vector, which we mapped with the mapping matrix to get our GC vector approximation. So now I'm curious, what happens if we instead feed 9/8 into this tuning of this temperament? Well, if we just work out the dot products again, we get -1, 2, and then that maps to -3, 2. Wait, that's just 9/8 again. So this one just maps to itself? It's got a bit of residual self-image, I guess we could say. Seriously, though, we can call this an unchanged interval of the tuning. This is a real thing. You may have noticed that this -1, 2 is actually the exact same GC vector as we got for 10/9. In other words, it's the temperament, it's the mapping that decided that 10/9 and 9/8 become the same pitch here. And then it's the tuning, the generators matrix, that decided after they got mapped to the same pitch that this pitch becomes 9/8. So here's a new generators matrix, and this one represents the tuning where 10/9 and 9/8 instead both get sent to 10/9. So in other words, this is where 10/9 is the unchanged interval of the tuning. But you might be thinking, if we're going to map 10/9 and 9/8 to the same pitch in this temperament, wouldn't it be better if instead of mapping from there to one or the other of them, we play nice and fair and map that pitch to something halfway in between them? Well, we can do that too. And that happens to be the quarter comma tuning we looked at in the beginning. This is the first actually good tuning we're looking at. The other two tunings we saw were a bit extreme. And also here for the first time we have rational numbers as entries in the matrices. We have a 1 over 4 in the generator's matrix, which times 2 in the GC vector leads to a 1 over 2 in the tempered PC vector. No problem though. Remember these counts are exponents. So a negative 1 means in the denominator, and a 0 exponent we can ignore, and a 1/2 means a square root. So this is just square root of 5 over 2, which is approximately 1.118. You'll recall that 10 over 9 was 1.111 repeating. So this is a bit wider of an interval than that, and it's similarly narrow from 9 over 8. So we have indeed successfully split the difference between 10 over 9 and 9 over 8 with this tuning. Great. Now for each temperament, such as mean tone, there are many possible tunings. Well, they're all within a very small range. You can't deviate too far from an octave and a fifth before a mean tone starts to sound like nonsense tone. To give you a sense for it, when the octave is tuned pure, then we're looking at a perfect fifth that's narrower than pure, but no narrower than 695 cents. That's only a 7 cents range of good tunings. It's important to understand that a temperament, as represented by a mapping, is abstract, which is to say that it doesn't specify a tuning yet. This is not a weakness, but a strength. Leaving the mapping untuned lets it focus on just one type of information, that type being, as we observed before, how it relates the different primes together. The exact tuning information is kept separately here in the generator's matrix. And so the mapping can only show you the door. You must walk through it, by choosing a tuning, that is. All right, we've come to it. The final matrix, the primes tuning map. Unlike the other three matrices, there's only one of these. This is not an example, it just is what it is. Well, at least this is what it is when you're only using the first three primes, 2, 3, and 5, because all the primes tuning map is a list of the primes, plus some extra stuff on the outside, meaning it applies to each prime. So what this primes tuning map does is takes a prime count vector and converts it to its value in cents. So that log 2 bit is what takes us to logarithmic pitch space. Again, we won't go into this into detail here, but this is essentially the mathematical way we get the system to realize that the distance from 1 to 2, and then from 2 to 4, and then from 4 to 8 is all the same distance here in this world. In other words, all octaves are the same. If we distributed the log across the entries, we get something like this. And this is easy to understand when we show the units. The primes tuning maps units are octaves per prime. So unsurprisingly, prime 2 is exactly 1 octave, and prime 3 is about 1.585 octaves. It's not 1.5 exactly, again, because of the logarithmic shape of human pitch perception. And prime 5 is about 2.322 octaves. Fine. Okay, so then the 1200 here is just for converting them from octaves to cents, and that's for convenience because it's generally easier to think in cents than it is in octaves. So that number has units of cents per octave, as you might imagine. And so if we distributed the 1200 then, the octaves and the units cancel, so we end up with cents per prime, and we get values that look like this. All right, so if we were to just take our interval and multiply it by p, that's our primes tuning map, that gives us the interval size in cents. But this doesn't have anything to do with the temperament. This is just its size in ji. We're getting this result because, well, we skipped right over G and M. G and M are the parts of the PGMI system that represent the temperament. More specifically, as we said earlier, M represents the temperament abstractly, and G, the tuning, makes it concrete by giving it the tuning. So one way to do this is to just go in order from the right, first multiplying the mapping in the interval I, giving us mi, which is our generator count vector. And then we multiply g times mi. That turns us back into a prime count vector, but tempered now. And finally, you map that with p to get your cents. Ta-da. But another way to think about it is to come from the opposite direction. Matrix multiply together p and g first, and this gives us a thing that we could call the generator's tuning map, with a little bold g, since it's a map with units of cents per generator. In fact, many RTT people don't even think about p and big italic g. That is, they don't think about the primes tuning map in the generator's matrix. They just think about this generator's tuning map. In other words, they don't worry about how the generators break down into their prime factorization, such as we see in the big italic G, since so often it's irrational anyway. Instead, they just choose their sense values by ear to their personal preference, or they might use a machine to compute the mathematically optimal values for the generator sizes. Whatever the case may be, we may keep coming at this problem from the left, further premix things, combining this little g with the m, and then you get something called T for temperament tuning map with units of cents per prime. And this thing works just like P and looks almost exactly the same too. The difference is it gives the interval in cents under the temperament. So in this temperament, the small whole tone is made about 11 cents sharp. And so we've now seen how PGMI lets you go from an interval to its size in cents in a temperament. And thus, we've completed our training session. You can now say, I know RTT. And I'll say, show me. And I'll leave you with one last thought. Sooner or later, you're going to realize that there is a difference between knowing the middle path and walking the middle path. Thank you for listening.